Hi guys, to continue on day one, we didn't get finished this example number 4. It's one of those special cases where there's an infinite number of solutions. If we wanted to look at a visual, what it is that paddle wheel idea. So it's this example right here. Everything along that line would be that black line would be points that are simultaneously in the green plane, the blue plane, and the red plane. Or we have lots of points that would work into all 3 equations. And the idea is it's not infinite points, meaning every point, every ordered triple. It's infinite points that have a pattern. We will work on finding that pattern too. All right, so back to example 4. We got started a little bit on the first video. We have here an XY. We have here, bottom one's an XY, top one's a YZ. So we need another XY or YZ. We could call that equation 4. So let's go through a number. That is 1, like we have been doing. That is 2. And that is 3. So my thought was to combine 1 and 2. So let's take 1. X plus y minus 3z equals -1. Let's take 2, and we're going to multiply it by -3. So -3y plus 3z. Yep, that's what's going to happen. We're going to get the z to drop out. 0 times anything is 0. So we'll call this equation 4. X y minus 3y is minus 2y. -1 plus 0 is -1. So now we've got equation 4 is an xy. Equation 3 is an xy. If I put these together right here, equation 3, -x plus 2y equals 1. Equation 4, x minus 2y equals -1. You could probably see where we're going with this. On the left side, just like when there's no solutions, the x cancels out and the y cancels out, but the main difference, the constants cancel out. When you get a 0 equals 0 combination, then that means infinite solutions. But we're not done. We now have to do 2 things. We have to find the pattern, and we have to find the infinite solutions, one ordered pair. One ordered triple. So here's what we're going to do. We're going to take this equation right here, number 4, and we're going to solve for x in terms of y. X equals, that's easy, bring the 2y over, 2y minus 1. And then we're going to take equation number 2 and solve for z in terms of y. No y in terms of z, either way. It says y minus z equals 0. So y equals z. So I've got the pattern right there. Between this and this, what do I know? Y and z have to equal each other. So I'm going to call them both y. So that means the ordered triple has to have the same number here as here. And x has to be 2 times that y minus 1. And so now let's just pick an ordered triple that fills that pattern. I'll pick the number 2 for y. That means z has to also be 2. 2 times 2 is 4 minus 1. That means x has to be 3. That's just one example. If I go back into all 3 of these equations, it'll work. I'm going to specifically go into 1. X plus y minus 3z equals -1. X plus y minus 3z equals -1. That pattern better work. That order triple better work. 3 plus 2 minus 3 times 2 equals -1. 3 plus 2 is 5. 5 minus 6 equals -1. Check. So again, there's infinitely many solutions, but they all have to be this pattern, and there's one specific example in the red. All right, So those are the special cases. Let's get back to one more normal example. That is a unique point. Again, our strategy with variables, equation 1, equation 2, equation 3. And again, I'm telling you there's a unique ordered triple. So what are we going to do? We're going to go from 3, 3 to 2, 2 to 1, 1. Take a look. I see 2 as an xy. Man, I think I'd like to get another xy. So I'm going to combine equation 1 and equation 3, and I want to get the z to drop out. How do I do that? Well, let's take equation 1, multiply it by 5. 5x minus 10y plus 15z equals 45. Let's take equation 3 and multiply it by negative 3. Negative 6x plus 15y minus 15z equals, what's that, negative 51. Just what we wanted. Equation 4, 5x minus 6x is negative x. Negative 10y plus 15y is 5y. 45 minus 51 is negative 6. Take a step back, catch your breath for a second. Equation 2 and equation 4. I'm going to take 2, leave it alone. I'm going to take equation 4 and negate it. Nice and documented, nice and organized. X minus 5y equals 6. X's are now gone. Negative 2y equals 2. I love it. Y equals negative 1. So now we can back substitute. If y equals negative 1, I'm going into equation number 2. Negative x plus 3 equals negative 4. Shoot that negative 1 in there. Negative x minus 3 equals negative 4. Add the 3 over. Negative x equals negative 1. X equals 1. Now I have both x and y. I'll pick equation 3. 2 x minus 5 y plus 5z equals 17. What did we say 2 was? Or x was a 1. What did we say y was? A negative 1. 2 plus 5 plus 5z equals 17. 7 plus 5z equals 17. Subtract the 7. 5z equals 10. Z equals 2. Ordered triple written as an ordered triple. X, comma, y, comma, z. And again, the only ordered triple that would work into all 3 original equations, the intersection of those 3 planes to that unique ordered triple, starting in 3 space at the origin, middle of the room, left 1 to the, x equals 1, 1 to the right, negative 1, y is down 1, positive 2 is 2 forward. All right, great job, folks. That's our day 1. What we're going to move next to, starting tomorrow, day 2, is we're going to get rid of our variables and we're going to do the same processes of solving systems, but we're using what's called a matrix.